Hello students, I am Isha Nagaratta. In today's video, I will be discussing about coordinate system. So let's start. Now what do you mean by a coordinate system? So a coordinate system is a system of measurement of distance and direction with respect to rigid bodies. So whenever we are dealing with magnitude as well as direction, we consider vector quantities. Now this is a system which comprises of coordinates as well as a reference point. Now let's see what is the function of these coordinates, or what do these coordinates represent. So these coordinates, they serve as a purpose of reference of direction of motion, and what is the role of origin, or what is the purpose of this origin. So this serves as a purpose of reference for the magnitude of motion. So coordinates basically are related to direction, and origin will serve as a purpose of reference for magnitude. Let's see what are the types of coordinate systems. So there are majorly three most common coordinate systems, namely Cartesian coordinate system, which is also known as a rectangular coordinate system. Then you have cylindrical coordinate system, and lastly we have the spherical coordinate system. So in today's video we are going to study these three coordinate systems. So let's start with the first one, that is the Cartesian coordinate system. Now let's see what this Cartesian coordinate system is. So in this system there are three axes which are perpendicular to each other, and the point where all these three axes, that is x, y and z, the point where three of them meet is known as the origin, or their intersection point is known as the origin. Now the Cartesian coordinate system is also known as a rectangular coordinate system. It is the easiest of all. So this system is the most convenient, and it is easy to visualize. It is associated with our perception of motion in day-to-day life. Comparing with the other two types of coordinate system, this is a system which we can imagine or visualize very easily. So let's see what this Cartesian coordinate system is. So the first thing we'll start with is, we'll just see how a point is represented in a Cartesian system. So you can just see that there are three axes, x, y and z, and there is a point A shown here, that is x, y and z. So x is the x coordinate, that means the distance of the point from the x axis. Y coordinate is the distance of the point from the y axis, and z coordinate is the distance of the point from the z axis. So any point in the Cartesian coordinate system, it is the intersection of x is equals to constant. We've taken a constant x plane, a constant y plane and a constant z plane. So intersection of all three distances will give us a point, and which is represented in a Cartesian coordinate system as x, y, z. Now let's see the next thing in coordinate system, that is unit vectors, because we are dealing with the direction also. So x, the distance of, you can just say the unit vectors in Cartesian coordinate systems, they are with respect to the positive x, y and z axis respectively. So ax is with respect to positive x, ay is with respect to positive y, and az is with respect to positive z. So the unit vectors in the Cartesian coordinate system are ax, ay and az. These unit vectors are always normal or perpendicular to the respective surfaces as they increase in the direction of coordinates. Now let's see the third thing in coordinate system, Cartesian coordinate system, that is known as the differential length. Differential length means, suppose I have considered a point x, y, z, a point P having coordinates x, y, z. Now suppose I say that x coordinate of the point P is increased by dx. So I just increase only the first coordinate by amount dx. So there will be a change in length dx. Similarly, if I increase the second coordinate by a small amount dy and the third one by a small amount dz, I will be getting the differential lengths dy and dz. That means my point has changed. It has relocated along the x-axis, y-axis and z-axis by small amounts dx, dy, dz, and hence I say that differential lengths in a Cartesian coordinate system are dx, dy, dz. So dx just indicates how much the point has shifted along the x direction. Next, we have differential areas in a Cartesian coordinate system. So here in the diagram, I have shown a point P dash, wherein I say that P dash is obtained by shifting or by increasing the x coordinate by amount dx, by increasing y coordinate with an amount dy, and z coordinate by an amount dz. So I have the coordinates of P dash as x plus dx, y plus dy, z plus dz. Clear? Suppose I consider only the first two, because area is a multiplication of two units. So suppose I say that I consider the xy plane, wherein the x and y coordinates have shifted. So along the xy plane, I get a differential area dx dy. So I say that differential areas in the Cartesian coordinate system are represented as ds1, that is differential area across the yz plane where x is a constant. So only y and z vary. So I have dy dz where x is a constant. Similarly, ds2 I have as xz along the xz plane when y is a constant. So that area is dx dz. Similarly, the third area dx dy along the xy plane where I consider z as a constant. So differential area would be dx dy. This is just a brief about the three differential areas. So only the surfaces are shown. The first one shows the xy plane when, the first one shows the yz plane when x is a constant, second shows the xz plane when y is a constant, and third shows the xy plane when z is a constant. So this is helpful to determine the differential areas. Now we move on to differential volume. Volume means if I multiply all the three differential lengths dx, dy, dz, I would be getting the volume dv in a Cartesian coordinate system as dx into dy into dz. Next we have vector differential length or the differential vector length pp dash, which is the result of the three increments in the three respective directions, that is dx, dy and dz. So I have pp dash. P dash was a point x plus dx. So distance, how much it has shifted in each direction. So pp dash is equals to x plus dx into ax is the unit vector in positive x direction. Then I have y plus dy minus y into ay plus z plus dz minus z into az, where az is the unit vector in z direction. So this gives me pp dash is equals to dx ax plus dy ay plus dz az. And this pp dash is represented as the differential vector length, which is known as dl cap. That is equals to dx ax plus dy ay plus dz az. So this is how we represent the differential vector length in a Cartesian coordinate system. Now let's discuss the second type of coordinate system, which is known as the cylindrical coordinate system. So in this system also a point is obtained by the intersection of three mutually perpendicular plane surfaces. I would say that in a cylindrical coordinate system, all the three surfaces are not parallel. One of them is cylindrical and the other two surfaces are known as plane surfaces. So let's just understand with a small diagram how do we represent a point in the cylindrical system. So suppose I consider the three axes. Suppose I consider this as the x. Suppose I consider this as the z, and suppose I consider this as the y. So this represents the xy plane. I just consider a point P over here. And I say that the distance of this point from the origin is, say, r. And if I say this angle, so this point, the position vector of point P, suppose it is making an angle phi with respect to xy plane, and I say that this point is at a height z. So how will I represent this point? I will represent this point as r phi z. I hope this is clear. Suppose I say I have a point P which is at a height of say 4 meters and it is making an angle of 30 degree with the xy plane. So such a point can be represented as r phi z. So now I'll just show you a small animation wherein the cylindrical coordinate system will be clear to you. So let's just start with this. So you have a constant surface r. You can just see that the position vector is moving along the xy plane. Then you have a constant phi surface, because phi is the angle which can change along the xy plane, and this is a constant surface z which represents the height. It varies from minus infinity to plus infinity. So this is how the cylindrical system is denoted. This is the point in a cylindrical system wherein we have two constant surfaces and one curved surface. So the unit vectors are AR, A phi, AZ respectively along R, phi and Z. Differential volume, we'll be discussing it shortly. So this represents dr, dz and r, d phi, and then we have differential area also, which is just like this. Clear? So now we'll just move ahead and discuss each one of them properly. So point in a cylindrical system, I hope the cylindrical system which I explained you is now clear. Suppose I say any point in the cylindrical surface is at a distance r, the position vector which we discussed. So r is a constant surface. Now any point on this plane has an angle phi, so we take phi as a constant plane. To obtain a point, we take another surface z, which is the height, and hence we represent a point in cylindrical surface in a cylindrical coordinate system as r, phi and z. Now let's see what are unit vectors in a cylindrical system. So unit vectors are represented as shown in the diagram. You can just see that you have a phi along the xy plane, then you have ar, that is the position vector of the point, and az along the z. So unit vectors in the cylindrical Cartesian system are ar, a phi and az respectively in each direction. So I would say that these unit vectors, they are always normal to the respective surfaces and they increase in direction of the coordinates. Now let's discuss the differential lengths in a coordinate system. So suppose I know the point. A point is r, phi and z. So suppose for a point I am increasing the first coordinate. So I am increasing r by dr. I would get a differential length dr. But suppose I increase the second coordinate. Now what is the second coordinate? It is an angle. So suppose I increase the angle by phi, d phi, I would be getting an arc. And how do I obtain the length of arc? It is the radius multiplied by the angle. And what is the radius? We have considered the radius as r because r is our position vector. So the arc length would be r into d phi. And the third coordinate, suppose increases, you will be getting a increase in length as dz. And the differential lengths in a cylindrical system are denoted as dr, r d phi and dz. dr is a plane surface, r d phi is a curved surface because change in angle gives us an arc. So we have taken arc length. And the third one is again a plane surface. Now let's move on to differential areas in a cylindrical system. So these are the three surfaces which were also shown in the animation. You can just see the first one where r is constant. Suppose I consider r as a constant, I would be getting the next, the second and third, that means r d phi and dz. Suppose I take phi as a constant, I would be getting dr dz. And suppose I take z is equals to constant, I will be getting dr into r d phi. That means I have the three differential areas as r d phi into dz when I have r is a constant, dr dz when phi is a constant, r dr into d phi when z is a constant. Let's discuss the differential volume in a cylindrical system. So it's just the multiplication of all three differential lengths. So differential lengths, we have r, dr, we have d phi and we have dz. So that gives us dV is equals to r dr d phi dz as the differential volume in a cylindrical system. And the differential vector length dl, that is the, you just try to recall the Cartesian coordinate system wherein we found out p dash, right? So suppose I consider a point P and suppose I consider a point P dash wherein I have changed all the three coordinates. So the differential length p dash, that is we denoted as dl, it is equals to dr into ar plus r d phi into a phi plus dz into az, where ar, a phi and az are the unit vectors normal to the respective surfaces. Now let's discuss the third coordinate system, that is known as the spherical coordinate system. So let's first see what a spherical coordinate system is. A spherical coordinate system is a three-dimensional space where the position of a point is specified by three numbers. Which are these three numbers? It's a radial distance of a point from the fixed point, that is origin. Then you have a polar angle and then you have an azimuthal angle, that is an angle of projection. So I'll just explain you shortly what this means. But before that, let's have an idea which will give you a better understanding of spherical coordinate system. So we have the point represented as r, phi and theta, and these are the three unit vectors in respective directions. This is how we determine the differential volume. Just imagine a portion of the sphere. This is what is the meaning of differential volume. Clear? The three dimensions, multiplication of them, and this is how differential areas are represented. So we'll be discussing it briefly, and let's start with what a spherical coordinate system is. So I'll just say what a point is represented in a spherical system. I'll just explain you briefly. So here also I just draw the three axes. I draw the three axes like this. So this is my x, this is my y, and this is the z axis. Is that clear? Now suppose I take a point P and I say that position vector of this point. So this is the position vector of the point I represent as r. This angle which it makes with the z-axis is known as the angle theta. And suppose I take a projection of this point. Suppose I take a projection of this point along the xy plane and I say q. So this is the position vector of the projection of P on the xy plane. And suppose this projection makes an angle of phi with the xy plane. So here I have two possibilities. The coordinate of P, I have r as a position vector. Then r can rotate with respect to z-axis by a change in angle theta, and its projection which I have taken on the xy plane, that is also making an angle of phi with the xy plane, and hence I can just represent my point P as r, theta and phi. So this is how we denote a point in the spherical system, and the three respective surfaces are shown in the next diagram, where you can say you have a phi equal to constant surface, r equal to constant surface, and theta is equals to constant surface. But here just keep in mind the position vector will make an angle of theta with z-axis. That means it is rotating about the z, and its projection is also rotating about the xy plane by an angle of phi. So I can simply say that I just consider this as a part of the sphere, just a portion of the sphere. So I represent a point in the spherical system as r, theta and phi. Now let's see what are what are the unit vectors in spherical system. So the unit vectors are ar, a phi and a theta along the perpendicular surfaces, r equal to constant, theta equal to constant and phi equal to constant. So these are the unit vectors in a spherical system. Now let's move ahead and see what are differential lengths in a spherical system. So here we have three coordinates. I have a coordinate r, theta and phi. So suppose I say that my point P, wherein I have represented P as r, theta, phi. So suppose the first coordinate is increasing by dr. I would get a small differential length dr because that is a position vector. Suppose I say the second coordinate is increasing. Second coordinate is theta. If that is increasing by an angle theta, d theta, it will result in an arc, the length of which is given as r d theta. And suppose I say the third coordinate, that is phi, which is obtained by the projection of point P on the xy plane. So suppose if the third coordinate changes, it will again result in an arc of radius r sine theta. Why did we take r sine theta? Because that is the projection of a point on the xy plane. So radius is r sine theta, and the third coordinate is changing by an amount d phi. So what will be the arc length? It will be r sine theta into d phi. And hence I get the differential lengths in a spherical system as dr, r d theta and r sine theta d phi. Now let's move ahead and discuss the differential areas in a spherical system. So just consider the first one where I have r as a constant. So I have the I have the surface wherein I have r d theta and r sine theta into d phi. Similarly, the second one shows when theta is equals to constant. So when theta is equals to constant, we have dr and r sine theta into d phi. And the third one where phi is a constant, we have dr and r d theta. So I have the three differential areas. When I consider r as a constant, my differential area would be r square sine theta d phi. If I consider theta as a constant, it will be r sine theta dr d phi. And if I consider phi as a constant, it will be r dr d theta. Let's see how do we represent differential volume in a spherical system. So it is multiplying all the three differential lengths. What are the three differential lengths? You have dr, you have r d theta, and you have r sine theta into d phi. So I get the volume dV as r square sine theta dr d theta d phi. Clear? And what are the differential vector lengths? So it is dr ar, where dr is the change along the unit vector ar, plus r d theta into a theta, where a theta is the unit vector in the plane of theta, and r sine theta d phi into a phi. This is how we represent the differential vector length in the spherical coordinate system. So today we have seen the three important coordinate systems, wherein we started with the easiest one, that is the Cartesian coordinate system. Then we moved on to cylindrical coordinate system and the spherical coordinate system. So basically we have seen how do we represent a point in each of them, what are the unit vectors, how do we find differential lengths, differential area, differential volume, and the unit differential vector length. I hope you have understood all the topics I discussed today very well. Thank you.